And of course you have to look at my face up close. Sorry.
It's harder to watch them though.
I know. Well, when they're short, when my nose is in the way.
Oh, well, just because on your titles you don't have the number, like the sequencing order, so then you have to like open one up, go look at it, go, oh no, that's one, I already looked at that, go back and
No. On the schedule page, it takes you right to the start one.
The first one, and they don't auto string through.
They do.
Not on my computer.
Oh, they do though. I set them on a playlist.
I mean, they did last time.
They should.
Not this term.
They should. They are on mine because I've done a playlist. And what I do is I put them into the playlist for 244, and I link the first one in that day. And then on the right side of the screen, you'll see the next one. So I don't know what's going on. Check your settings, I guess. That's the best easy answer I can give you.
All right.
But that's, I mean, it is working.
But
I know it's working.
you did start labaling them down in like the comment section at
Part 1, Part 2, Part 3.
Yeah, so at least I could do that.
Well, of course, but they should be also showing on a sidebar. There's some way you can close it and open it.
But well, there is, but you can't tell which one is which. They're not automatically putting them in order.
They are. Well, let me just show you.
All right. Sorry, guys. This is like the predominant way that I'm watching lectures.
Well, I mean, and it's good for everybody in case you miss. I mean, it's good to follow it. Here we go. Let's just grab that schedule. All right.
So that was 243 though.
That's okay. It's the same schedule page. So here's the first day of 243. So here they are over here. 1, 2, 3.
But that's 105. And
well, I mean, but I do all the same way.
Okay.
They're all done the same. Here's 244.
All right. Yeah.
Hey, it's freaking fantastic.
Hey.
Mine doesn't look like that.
So I'm guessing it's a setting issue then, Madeline. I'm guessing it's just a setting. So just mess with the settings, I guess.
Okay.
Because I'm doing exactly the same I did it last term.
Yeah, I'm hunting and pecking. I ended up watching a whole lecture from last Wednesday and then going, oh, wait a minute, what were you talking about cards? And then realizing that I'd missed part of the lecture from the first day. So.
Well, I wish I had more to tell you than just check
That's
your
okay,
settings.
it's okay. I'll deal with it. Moving on.
All right. Brandon, would you mind? Thanks, sir. Now, we're going to focus on the exact same 2 parameters all term. I think that, Kate, you mentioned that a 243 student once told you, you've heard that 244 seems easier than 243. I think a lot of the reason is we focus on the same 2 things over and over and over again and keep going back and forth between them and analyzing them in different ways. Like we'll estimate 1 parameter, then 2, then 3, then 4. We'll estimate one proportion, then 2, then 3, then 4. We'll estimate 1 average, then 2, then 3, then 4. And I think that's why it is. So all the proportions are dealt with certain ways, and all the means are dealt with. Right now we're dealing with proportions, percentages. Percentage of time we get hits, for example. Since it's discrete, we tie it back to the binomial distribution. You guys are going to have this whole PowerPoint if you don't already linked up on the schedule page. I think it's already linked from last week. I think. If it's not, I'll make sure it is. From the binomial, I never made you memorize these formulas. There was no need to memorize them back in 243 because you could run dist fill and get them. You figured them out without realizing you figured them out with like chickens. When we did the chicken experiment, you would automatically figure out that one. I didn't bother having you figure this one out because it takes 3 pages of mathematical proof to figure out. And if you're interested, it's in the original page if you want to see it. I didn't believe it. Harrison's like, I am on that right now. I didn't believe it when my prof put that up on the board. He's like, yes, the standard deviation of binomials, radical MPQ. I said, well, why? How does that even make sense? First of all, N is your trials, P is the chance of success on any given trial, and Q is the chance of failure. It's the complement of success. I think we talked about that briefly in 243. If we didn't, it's not a big deal. And I said, why? Like, that's so pretty. Like, how can it be that pretty? Especially when the computation for a standard deviation is so complex. Think about Bert and Ernie, right? This minus this, this minus this, this minus this, square them all, add them all up, divide by blah, blah, blah. It just so happens that with a binomial, when you do that, algebraically, it collapses down to this. And that was mind-boggling. I had to sit down and prove it for myself, and there it was. So you see my work online if you want to see it. But anyway, that's where all of this starts. All of this starts from the average and the standard deviation of the binomial. Now those are parameters, yes? I call them mu and sigma, because they're parameter values. And that's awesome, if we actually knew what the parameters were, which we don't. They're out there floating around, so the idea is we estimate them. So here's the deal. This guy right here, the average is wonderful, but we're not going to have that. We're going to have this little guy right here, P hat. He's our little friend. Now I've written it formulaically, not that you ever have to use a formula to write this down, because you're going to have technology do it for you. But can you see how this guy right here is related to that guy right there? Take a look at both of them and see if you can see some similarities between them.
Oh, yeah.
P hat x over n, and mu is n times p. Do you see a mathematical relationship, how they're similar?
Basic algebra.
Okay, so they both have an n in them. Notice where the n is here. Yeah, it's right there. And essentially they serve the same purpose, although n up there would be more of a parametric n, this is more of a sample n, but the same number of trials. Think of it that way. Little p hat, who's he like? Who's he like up there? Michael! Or, two Michaels. Yes, P. I don't know which Michael said it, but yes, it's essentially P. P hat is the sample version of P, which is the population version. And the only difference is this guy is mu, yeah? And this guy is X. But they're related too. Mu would be the average number of successes in the population. X would be, if you will, the average number of successes in your sample. We don't call it mu because it's a sample, so we just call it X because it's a sample value. Do you see how the equation is essentially the same though? If you took this bad boy and multiplied it by both sides by n times p hat equals x, just like n times p equals mu. So they're the same equation, if you will, just solve for n, Renee, go!
What if there's only one trial?
Go get more. That's a great question! That's a fantastic question. What if there's only one trial? Here's a penny, spin it one time and estimate the probability of getting heads. What is the potential problem with that?
100% of the time.
Or 0. Right? You spin one penny and see what happens. It's either, I'm 100% confident that the chance of getting heads is between 0 and 100. And you're done. There's no statistic due because you only have one trial. You gotta get more. And there's a set limit for a minimum, which we'll get to today, thank you. Yeah, there's a minimum, and there's a better minimum than minimum, but we'll get to both of those today, I promise you.
And it's not possible to get an average with a single number.
Well, mathematically you can.
I mean, you could.
Mathematically you can, it's just you shouldn't. Because it's
logically, it doesn't make any sense.
because of this magical thing called a margin of error, and you're about to see why we like larger samples right here, it becomes useless. You can do it, but it's just like I said, between 0 and 100% of the time, you're going to get hit. Thank you. Thank you very much. I could have stayed in bed and gotten that answer. Right? You see what I'm saying? So, yes, we'll get to a bare minimum and then a better bare minimum today, I promise. Thank you. Great questions. Keep those coming. Keep those coming. Now, Michael, you asked earlier about 2 standard deviations being a margin of error. Thank you very much. I want to break it down to just one standard error real quickly. One standard error. A standard error, and it's okay if you don't remember this from 243. It was one of the last things we did in 243. A standard error is the sample version of standard deviation. It's the inferential sample standard deviation. So there's a thing called a sample standard deviation. We call it S back in the day. Okay, and we're going to use him. We like him. We like him a lot. We're not going to use him for these guys. We're going to hold him for continuous data. We're going to hold him for continuous data. We're going to like a different one for discrete because it's binomial. Remember, we never used S for binomials either. We got away from him because he's more for continuous. But the idea is, a standard error is an adjustment, and this is not important to memorize, but it's important to hear once, and then hear every day when we talk about it. Standard error, if you remember from 243, shrinks as your sample size gets larger, right? You get precision, you get better precision as your sample size gets larger. And we figured that out in class. The more times we rolled dice, those bell curves pulled in and rose up. Yes, that was very, very nice, wasn't it? Yes, we like that a lot. We're going to experiment with that a lot in this class. So the idea is we need to adjust this, because if you look at this mathematical formula, as n gets bigger, right, what's going to happen to sigma? Mathematically. Don't look down here, look up here. This is 243-ish. As n gets bigger, what's going to happen to this whole quantity? It's going to get bigger. Now, that was almost a trick question because I was just talking about how n gets bigger, precision gets, but that's down here. Here, as n gets bigger, this thing gets bigger. It's all on the same line if you think about it mathematically. And it kind of has to, because as n gets bigger, you're going to get more variability in the population because you're going to see more and more terms. So those extremes, those outliers, are going to start showing up. If they didn't in a small number of trials, they definitely will in a large number of trials. But we have to counter that somehow, mathematically, in a sample. And the way you do it, cleverly enough, and I'm going to talk about it here, I made a video to go along with it, in case you want to see the mathematics behind it. I also did a proof on the Richmond page. To get from here to here, essentially we divided by n. Essentially, right? We just took both sides and divided by n. Guess what? To get from here to here, you divide both sides by n. Now some of you might not believe that this divided by n equals this. If you don't believe it, and I encourage you not to, check out the video I posted off your homework page. There's a video off the homework page that walks you through the proof of it. I used to do it in class at 8:45 in the morning. It's not the right thing to do in class. So I made a video proving both this and why they're legit. So by all means, and if you don't want to watch the video, I've got a proof on the Richmond page that backs it up too. If you can't wait, we'll do it at break, happily. Everybody's taking 5, you can prove it on the board for you. But it's good mathematics, So this is one standard error. And Michael, you asked about, is it 2 times the standard error, 2 of them to get a margin of error? Usually yes, but in general, oh, that's a strange little subscripting I did there.
Yeah.
The whole word critical was supposed to be subscripted. I'll fix that. Let me fix it right now, actually, because right now it's confusing as hell. Hang on.
I'm really wondering about that.
Sorry.
I think it's kind of cool.
I don't know what that means. but-
Sorry. Hang on. Let me subscript the whole damn thing. There we go. That is much easier to look at. Okay. So, to turn it into a margin of error, you're going to take your standard error and then multiply it by what statistics calls a critical value. A critical value is a number of standard errors. I don't know why they call it a critical value. I mean, later on it makes more sense to call it that, but even for a margin of error. And those critical values depend on how confident you want to be in your result. JC's already told me 95% means it's 2. Boom, we know that. So this multiplier will be 2 for 95% confidence. And we're generally going to use that for our confidence level. I'm going to show you real quick. Don't write all this down. Here's kind of a common table, commonly used confidences, and their corresponding Z critical values. So if you only want to be 68% confident, roughly 2/3, go ahead and just use 1. Use 1 standard error. Because we learned that in 243, yeah? If you come in here to 1 standard deviation, you're only trapping that much of the curve. If you want to be more confident, make your Z critical bigger. So as your confidence goes up, the Z has to go up. Because
That's the standard deviation.
it's the number of them. Yes, ma'am. It's the number of those. And I'm going to start calling them standard errors if it's okay.
Okay.
Only because we're going in for, it's the same thing, JC. I mean, honestly, you can call it whatever you want. But you're going to hear me keep calling it standard error because I'd like to keep putting it.
Critical, standard error, standard.
Absolutely. And you don't have to worry about anything after we do this one manually for the penny spins. Because technology is going to do it all for us. It's going to keep track of all those critical values based on how much you're confident. I don't want you guys getting bogged down. That formula it throws people off. You'll see why momentarily. It can throw people off. Did you catch this bit? I put for 95 it's 2, actually 1.96. You might or might not remember that from 243. It's not exactly 2. It's closer to 1.96.
Does the program do 1.9?
Yes, it does. It already lops it out to like 100 decimal digits of precision. So you don't have to worry about that either. So we'll go ahead and use 2 just to make life easy for ourselves, realizing the program will do it for us automatically. Make sense? Yeah. So now I think we have what we need. I want to come back to this momentarily. As far as, I want to drive home the point of what that 95% confidence means today to you guys. Because I want to make sure that you understand, okay, what does it mean to be 95% confident? Why not just go to why not get as close to 100% as possible? That seems better, doesn't it? And there's reasons why we don't. Go ahead, Kate.
Isn't that because then you're just doing more and more trials that you're spending money on, but 95% confidence is enough?
It's enough for standards, yes. It's a standard, like industry standard, yes. And that's one reason. Is sometimes it costs too much to go above 95%. There's more mathematical reasons too. We'll definitely get back to them. Lauren, go.
As we do more and more Z's,
Yes.
aren't we getting closer to, it's somewhere between 0 and 100?
Did you catch that? If you take it to the complete extreme, the higher you make Z, or the higher you make this confidence, the bigger Z gets, which means the wider your confidence interval gets, which gets us closer to we're now between 0 and 100% confidence. So you have to sacrifice usability with confidence. Again, where 95% seems to toe that line very nice. Thank you, Lauren, that was perfect. Mike, is that what you're gonna say?
Yeah.
Exactly, that's a good point, and that is a dance we dance, which is, again, 95%, we don't have to get dancing unless you want to. But that 95 does do a nice job of both. It also reduces a certain kind of error, which we'll get into in like 3 weeks. There's a couple ways to be wrong statistically, and we have to look at both of those ways, and 95 does a nice job of balancing both ways. JC, go.
Does it have something to do with the outliers too?
It does. It has everything to do with that, which we're going to get into today. And you'll see when we click on this link in about 15. I don't want to get, I was thinking about it, I don't want to do it right now. Because I think right now, yeah, you know what the hell, let's do it. Let's take it. Because of what Lauren just said, I think we'll actually, okay. So, this, I just made this up over the break. Hopefully it makes sense. Let's see if you guys can buy it. What you see here is I made up a population distribution. I made it skewed. I don't know what the hell I used. I think I used a Poisson distribution just to make it kind of saucy. So it's goofy, skewed. You have no idea. You don't know what it is. It's out there somewhere in the population. And I kind of grayed it out and put it in the background because you don't actually know where it's going to live. But you're interested in it. That might be, for example, the average temperature gain for a 6-month-old child who takes a certain medication. You might be looking at side effects of a medication. You're interested in knowing what the center of that distribution is, even though you don't know what the distribution itself is. So what you're going to do is you're going to draw a sampling distribution from that population. You're going to draw a sample, and you're going to analyze that sample. Now what I've done here is I've showed you the center sampling distribution, which, as you know, is the same as the population average, on average. Now, remember too, that sampling distribution is just as fictitious as the population distribution. The sampling distribution is the distribution of all possible sample averages. All of them. We talked about this in 243. On average, all of the sample averages average to mu. Exactly, JC's starting to laugh because he's like, that sounds great, except that you get one average. Yes. And the one average you're going to get is the center of this interval right here. See this guy right here? This is a confidence interval. It's a confidence interval. It's set at a certain level of confidence. We're going to play with that momentarily. Okay? So this is the result of your study. So you don't get to see any of this stuff that's up here. All you get is this interval right here. Now in that particular case right there, did your interval catch the average? It did, just barely, but it's in there, isn't it? It just barely caught it.
Isn't it? It has to be.
95% of the time. Or 98% of the time. Or 68%. That's the kicker. So watch this, JC. Every time I hit F9, I get a new interval. Now notice, quite a few of them, oh, but look at that. There's your outlier. There's your outlier. So remember, you don't get to see any of this up here. It's existing in the world, and you're studying it. What you get is this snapshot. And unfortunately, you just missed that one right there, didn't you?
I don't understand how you do that.
Because of randomness.
Yeah, but if you extend your CI, whatever,
Why don't we do
then
that?
you're trying to.
Mhm.
But,
Now, hang on a second. JC, can you give me 30 seconds on that?
yeah.
29? Oh shit, waste of time. Okay, so right now, friends, what I'm doing right now, I'm holding down F9. As you did many, many times in 243. Okay? What this is doing is,
I like the
it's,
cumulative down there.
say that again.
It's keeping track
Yes,
of
it's
how
keeping
often-
track of how often we catch the parameter.
And unfortunately, most
We suck
often-
right now,
yeah.
yes? We suck right now because the interval's too narrow. So, Renee, go.
I was just saying that looks dangerous.
That is dangerous. You're rocking at about 38% confidence right now. You try that crap out in the world, you get fired. You have to raise your confidence in this case. So, Laura brings up a good point. She says if you raise it too much, essentially it's going to cover the entire distribution. Then you got 100% confidence, but it's also 100% useless. So the idea is not to make it so narrow that you miss it all the time. Exactly, but not to make it so big that it's useless. So let's bump the confidence-o-meter up a little bit. Okay? Now notice the interval's got wider. Notice the interval's got wider? Now, I'm not going to reset everything. Maybe I should. Yeah, let's reset everything. I made a macro for this, but it kept making my machine hang, so we're just going to do it old school. All right, here we go. Let's see how we do this time. Much better confidence, yes?
Yes.
Still too low. Still too low. Let me say stop it somewhere in the middle. Yeah, that's almost dead center, right? Now you can see why the confidence is still a little bit low. Check out that interval. I tried to make it roughly to scale. The sampling distribution you're going to get is bell-shaped, always. It's always bell-shaped. And these guys right here are ticked off standard deviations. Ticked off. They're standard deviations marked with tick marks. There we go, not ticked off. I guess they are ticked off. Notice how the interval's a little narrow of 2? It's a little shy of 2, isn't it?
Yeah.
It's between, thank you, it's between 1 and 2, isn't it? Whoever that was, thank you. It's between 1 and 2. 1 would be confidence of 68%, 2 would be confidence of 95%.
Yeah, it looks like a 1.8.
It's about 1.8% right now, ish, somewhere there. So let's just bump it out a little bit further. A little bit further, a little bit wider. How's that looking? A little bit better? Let's reset this bad boy. All right, let's see how we're doing now. Oh, that's much better. Much, much, much better. And we hold this bad boy down the stapler. Let it go for a while. Because that's what you do when you don't take Visual Basic. I think, anyway. Is it still going? No. Somebody remind me to take Visual Basic at some point this term. You get the point. Stapler. You get the point. Oh, it's working. No, it's not working. Ish. So the idea, though, is all the stuff above the line you will never see. That's the problem, yes? You never see what's above the line. You only see what's below the line. So the idea is to make sure that what's below the line is catching what you're looking for a set percentage of the time. That's what 95% confidence means. It means 95% of the time we're going to catch what we're trying to catch. And 5% of the time we're going to miss it. And that's okay. You have to miss it at some point. Even if you make it 4, 5, 6 standard deviations wide, you're going to miss it sometimes. Lauren, go.
You're catching your entire bell.
Say that again. You're catching 2 standard deviations of it.
Right.
1.9.
All of your
Except for the outliers.
In this case.
Right.
Except for the outliers, yeah. You know, I see what you're saying. I see what you're saying. Say that again. Well, hold that thought. Can you hold that thought temporarily, friend? Lauren said that doesn't seem precise. We have a fix for precision. Remember what the fix for precision is? What's the fix? Thank you for that, by the way. What's the fix for precision, Lauren? Somebody already said it today. More trials. And this, I didn't make this spreadsheet involve precision. The next one that we'll look at does. But as we up the sample size, what's going to happen to that bell curve, Lauren? It's going to go shoot, swoop. And then 2 standard errors shrinks down to like this. So you pick up precision with larger samples. I was trying to keep the sample size, if you will, exactly the same and only adjust confidence. Fair enough? That's a very good point. Thank you, sister. We'll get back into that today, but also this spreadsheet doesn't deal with precision, only accuracy. Is that fair? Do you guys see the difference between accuracy and precision as Lauren is laying out for us? Very, very nicely done. Very, very nicely done. The big thing is, though, you only get this. Oh, and Lauren, too. I never gave you a scale intentionally on this graph. This could be 1/4 of 1%. In which case we got tons of precision, or 1/10 of 1%, in which case we got more precision. So I'm trying to leave all that general as possible, so we only focus on the idea of what does this 95% confidence mean? It means, on average, you're going to nail that, what you're looking for, 95% of the time. Now, you don't do it with the confidence-o-meter in the world. You do it via calculation. I mean, the whole point of it is you don't use the sliding meter. Although sliding meter is pretty freaking rad. Right? When I discovered you that in Excel, I had a little happy dance. It's pretty awesome what you can do with those. And every spreadsheet I've made since then is full of those things because they're wickedly helpful in a class like this where you can use them to work. So anyway, let's get back to our pennies and see how our pennies deal with all this. Now, of course, our pennies have a distribution, and we don't know what the hell it is. It's out there somewhere. And our pennies have a sampling distribution, and we don't know what the hell it is. And it's got an average, and we don't know what the hell it is. But we can get one thing, yeah? And that one thing is this. We already have part of it. Which part do we have? We've got our p-hat. So the idea now is, let's build the rest of it. Yes? Let's build the rest, take 5, and then talk about it when we come back. Delete this. So, we're feeling pretty good. Brandon, if you don't mind, thank you, sir. Let's stop this.